Today we're going to talk about population models. But before we do that, let's take a few minutes and look back at what we've done. In particular, we've learned how to solve first-order differential equations. Well, word of warning, there's a lot of the first-order differential equations we can't solve. So perhaps it's more appropriate to say we've learned how to solve some types of first-order differential equation problems. So let's take a look at the different things and approaches that we have for solving. The first approach, separable. So what is a separable differential equation? Well, it's something that can be rewritten in the form y prime is f of x times g of y. Now, what does it mean to be separable? Well, the clue is in the name. Separation. So there's separation involved. What can happen is you can put the variables. So on one side, you only have y's. On the other side, you only have x's. Of course, I should pause and say there's nothing sacred about the symbols x and y, just tradition. So if you use x and t or any other two symbols, don't worry, same approach. Okay, so we've separated all variables over here of one type, all the variables over there of the other type, and now you integrate. And that gets rid of your derivatives. Life is good. And of course, you might say, okay, you've solved the differential equation, but you might not be fully done because you might want to rewrite it. So that's the last part, which is to uncomplicate. All right, so that's not so bad. Well, really, none of these are so bad once you get the hang of it. It's just good to remember what we do. All right, the second type, linear. Now, a linear differential equation is one that can be rewritten as y prime plus p of x y is equal to q of x. All right, great. Now, it gets its name because of the way y shows up. Namely, there's no strange functions of y. There's no y to a power. There's simply a y and a y prime. Say, okay, well, how does one go about solving such a differential equation? Well, the trick here is, how do we integrate this part? Well, the y prime, sure, it integrates to y, but how do you integrate this piece? Because we don't know what it is. And so the great aha, someone came along and said, ooh, if you introduce something new, and that's called the integrating factor, what you can do is multiply both sides by the integrating factor. And if you multiply everything by the same amount, it's the same differential equation. But by choosing wisely, you can get something that makes this left-hand side nice. Makes it a derivative, makes it something that can be solved. So then you're able to actually integrate. So in other words, what you end up with is, well, let's call our integrating factor rho. Some people call it mu. It doesn't matter, same philosophy. So after multiplying through, what you end up with is something that looks like the following. You say, aha, it's very clever, and just right means that this is the derivative of rho of x times y. And now the easiest thing to integrate is a derivative. And life is good, and off you go, off to the races. And on the right-hand side, everything is a function of x. And see, integrating the x part is not so bad in theory. It's integrating the part of y, because y is an unknown function of x. So that's why putting that y inside the derivative, great strategy, wonderful strategy. All right, the third technique is what's called exact. Now, what is this? Exact? Well, this is something that you can write where m, I'm going to think of this as a function of both x and y, times dx plus n times dy equals 0. There are other ways to write it. And, well, just because it's written like this doesn't mean it's exact. What you need is something special. Now, usually, most people will say, well, these partial derivatives, the derivative of m with respect to y and m with respect to x, line up. What that gives you is it says, oh, actually, what is really happening is that the left-hand side is a derivative. And so that's what's going on. When it's exact, we say, oh, really it came from a derivative. And derivatives are easy to integrate. So you might say, well, isn't that kind of a philosophy with linear too? Yeah, same philosophy. It says, hey, I can recognize there's a derivative in here, now I can integrate. And so for exact, what's the challenge? Well, the challenge is find f. Because once you find f, well, the derivative of f is 0, so that says, hey, our solution has to be some function whose derivative is 0, which is some constant function. And the way we do it, well, it turns out that m and n aren't just anything. They're partial derivatives of f. And since we have the partial derivatives of f, we can integrate, compare, and combine the parts to get f. All right, so those are our techniques. Now, you might say, okay, are we going to learn more? No, that's it. That's it. And you might say, well, can I do other things? For instance, we saw for linear, multiplying by the right thing could turn it into a right derivative. Maybe, is there a way if I have an expression like this, I can find some right multiplicative factor that turns it into exact? And the answer is theoretically, yes. Practically, no. So we're not going to go down that road. And so that's it. So the nice thing is you only have really 3 options. And so you can always try, does this one work? Nope. How about this one? Nope. How about this one? Nope. Okay, go back to the first and try again. Well, actually, there is a 4th thing, and you can see it here, which is you can rewrite things. So if none of the above are working right away, you say, well, maybe there's a way to simplify. Substitution is really about simplifying your differential equation, to rewrite it in something that's easier to work with. And you look for certain substitutions. There are some that are fairly common. There's the homogeneous substitution, and that's when you let your new variable to be y over x. There's the Bernoulli substitution, and that's when you let your new variable be y to the k. And those are the 2 common ones that we've talked about. Of course, there's many, many, many more possibilities, but generally speaking, these are the ones that we'd like you to know. Now, as you go out into the world and you start seeing differential equations out there, you might say, well, what do I do? How do I know what kind of substitution to make? And, well, it's hard to say, this is it. This is the one way that you'll get every substitution that will ever be out there. What you should do is you should say, okay, look for things on the inside and look for derivatives. So those are the 2 things that help you identify substitution. It's just a lot like integration in calculus. What I like to offer as a piece of advice is the following. Namely, if you see something, in other words, you say, oh, I wonder if maybe that could be something interesting. Well, try something. In other words, it's okay to not be 100% sure, but try things. Trying things are a wonderful way to make progress in math. You know, oftentimes people will be like, I've tried nothing, and I'm all out of ideas. And we're like, no, you haven't tried that much, because we promise you that the problems we give you are ones that we know can be solved. So try things. Trying is a wonderful, wonderful skill set to have in mathematics. So now on to the main topic for today, population. So we're going to talk about population models. Now, if we think about population, that's something that can change with time. And so this becomes a nice way to model things with differential equation, because we can talk about change. And you can really summarize it in the following way. We can say, well, look, change in population. So whenever you hear the word change, you can think of it as you have derivative. So this is our change in population. You say, all right, well, how does a population change? Well, there's really 2 things that can happen. there's our growth. In other words, population is somehow increasing. Now there's a couple things that it could be causing. There's some internal growth, and that's like, you know, when, well, that's a discussion you should have with your parents. So, okay, so growth, and then there's, we'll call it decline. So growth, there's internal growth, there's external growth, people coming in, decline again, there's just natural death, there's people leaving, and so you have these two forces acting on population. You're growing or declining. And so now I can say, look, the change in population, I combine these two things. Say, all right, great. So now, what do? Well, we say all we have to figure out is how are these factors coming into play? So a very simple model is to say, well, the size of the population will be proportional to our growth and also proportional to our decline. In other words, you know, a certain portion of the population reproduces every year. So that would be some constant times the population. So for example, if there's 1,000 people, there's a lot fewer births than if there's 1,000,000 people. Similar idea for deaths and shrinking. You know, we expect a small population not to have too many deaths. A large population will grow proportionally. So that could be something like a constant multiple of the size of the population. So we say, okay, well, in this very simple model, we can have our beta times our population and our delta times our population. Think of beta for birth, delta for deaths, or say, oh, hey, this is some constant times our population. And all right, so it's easier for us to write a constant, something like a symbol that looks like a constant. So a symbol like k. So change in population is k times p. Now we call this the exponential model, and we'll see why in just a moment. You may have already seen why in previous classes. This is not just this is not just for modeling population. You can model other things. So when you talk about things like radioactive decay, this also follows an exponential model. And in that case, what happens is that there's no growth, it's all decline. So k is a negative. So essentially the value for k tells you, well, if k is positive, you know, births are growing faster than deaths, things are going to get huge. If k is negative, it's the other way, things are going to get smaller. So this is a very easy, very simplistic, and in some cases very unrealistic model. But you know, you start with some easy things first. So let's find the general solution to this differential equation, p prime equals kp. So in other words, the model we just introduced. And we'll have an initial condition p of 0 equals p0, or some people call it p naught. And the question, what's the behavior as time goes to infinity for various choices of k? All right, so what do we have? P prime is equal to k times p. Now we can solve this as a linear, but it's really close to separable. In fact, it really is about as simple as separable can be. So let's do separable. So if we think about this, we can also write this as dp over dt is k times p, or dp over p is k dt. All right, now at this stage, we've separated. We see all the variables of one type on one side, all the variables of the other type on the other side. So we now integrate. And we get natural log of p is equal to k times t plus c. We can use the exponential function to get rid of the natural log. And if we do that, what do we get? Well, we get that p is equal to e to the kt, and then the e to the c becomes another constant, so I'll write that as c. Now remember, we do have an initial condition, so let's use that. All right, so p of 0 equals p0. That says p0 is equal to c e to the k times 0. Well, e to 0 is 1, so that's c. So now we know what c is. And so we can plug that in, and we get that our population grows like following. The initial population, e to the kt. And there we go. Great. Wonderful, wonderful. All right. Now, that's the first sentence done. We have found the general solution. So now we can say, well, why did we call it the exponential model? Because there's an exponential function. Ha! It's almost like it makes sense. Well, because it should. All right. Now, what happens for various choices of k? So let's start with k negative. And I mentioned this is the one which oftentimes shows up, for example, in radioactive decay. And, well, what do we see? So initially, we're at p0. And what happens to this e to the kt? So like e to the minus t. Well, the exponential function, when the exponent gets to a large negative number, is becoming small. So what's going to happen is it's going to exponentially decline. So it's going to shrink. So that's why in the long run, for radioactive decay, the radioactive elements will vanish. Of course, for some types of radioactive elements, when we say the long run, we really mean the long, long run. So it takes time. It all depends on k. The larger k is in terms of size. So a large negative number will be a very steep decline. A small negative number is a very slow decline. And so just because things go to zero, you still may want to know, like, well, how quickly does it go to zero? Because that can make a significant difference. All right, let's try now k equals 0. Okay, so what does that mean? Well, before we draw it, we probably can just sort of think about it, right? So we thought about k. So k was the difference between births and deaths when we talked about population models. So to say k equals 0 says that we're in that sweet spot where the number of births equals the number of deaths. So what's our population doing? Is it going up? Is it going down? The answer is no. It's staying flat. And we see that, right? Because we'll have e to the 0t, which is always 1 for any choice of t. And so what that does is it stays level. All right, so now what about a positive value for k? K greater than 0. All right, I'm going to give myself some space here. So here's our p0. And now we say, well, what happens? Well, we have e to a positive value, t. And what happens to the exponential function when you plug in positive numbers? And the numbers keep getting bigger and bigger. Well, the answer is the exponential function gets bigger and bigger, like really big. It's blowing up exponentially even, you might say. And so what's going to happen here is we're going to have a very quick rise. Initially, it might not be that big, but very soon it's going huge. Now, I mentioned this may not be realistic. Why not? Well, this says, look, you're going to just grow without bound. You can imagine bacteria subdividing. Okay, initially, yeah, they grow very quickly, but then there's a problem. There's somehow environmental limitations, and then they say, look, I can't keep dividing anymore because I've run out of resources. But here, this says, no, there's no problem. You can keep growing. And so if you start off with a single bacteria, in a matter of days, the whole earth would be covered in a huge layer of this bacteria. So there has to be other models that are maybe more realistic and take other things into account. And we'll get to one of those very soon. But first, let's do an example. When sugar is dissolved in water, the amount that remains undissolved after t minutes satisfies the differential equation a prime equals minus ka. So a for amount. And we'll think of t as time, so our variables are a and t. And notice we are in the exponential model. And it's already saying, okay, minus, so we should think of like exponential decay. So it's already capturing that. So if 25% of the sugar dissolves after 1 minute, how long does it take for half of the sugar to dissolve? All right. Well, what can we do? Well, one thing is we can say, all right, we can think of our model. We have A prime equals minus Ka. Now, we can do one or two things. We can rederive this, or we can say, oh, I know how this works. And since we just derived it, let's just say, aha, I know how this works. And we say, look, the solution to this looks like A, and I'm going to emphasize as a function of t, is equal to the initial amount, and then we'll say e to the minus kt. So this is just similar to what we just did. So let's just save ourselves some time. Say, all right, great. We want to practice not deriving it, we want to practice using it. So what do we have? We know that 25% of the sugar dissolved after 1 minute. So how long does it take for half of the sugar to dissolve? So we could say, all right, we know something about time is 1. So what do we know? The amount of sugar at time 1 is what? Well, if we think about it, so what is A? A is the amount that's undissolved. So 25% has been dissolved. So how much has not been dissolved? The answer is 3/4 has not been dissolved, right? Okay, you have to think about this, right? Because we have undissolved versus dissolved, and essentially they balance out. So we can say A of 1 is 3/4 of the initial amount. Now we don't know the initial amount, but oftentimes in these problems, it really doesn't matter what the initial amount is, because what will happen? Well, what will happen is you say, okay, so that tells us the following: 3/4 times our initial amount is A0 e to the minus k times 1. And now we're in good shape because the A0s cancel. That's why the initial amount is really not important. We could have chosen anything, or we could have just said, well, it's a symbol, and we'll put it as a symbol until it disappears. All right, so we now have 3/4 is e to the minus k. Taking the natural log, because, well, we really want k, we can say, all right, the log of 3/4 is minus k. Or, if we move the minus across, we could say that k is minus the log of 3/4, which is the same as the log of 4/3. All right, so there we go, there we go. Okay, good, good. Now, what comes next? Well, there's a couple things we could do. So here's one thing we could do. And one thing we could do is say, look, we know minus k is log of 3/4. I'll just point this out. What does that tell us? It tells us that a of t is A0 e to the, replace minus k by log of 3/4 to the t, but then I can bring the t out here, and so it becomes A0 times 3/4 to the t. That's one thing you can do, or you could just say, look, I'll just leave it with a of t is A0 e to the, well, I can say log of 3/4 or minus log of 4/3, whichever one I'm in the mood for. These are the same, whichever way you want to write it. So the point here is we've solved for k. Now, why did we want to solve for k? Well, because ultimately, what are we after? We're trying to answer a question, and k was an unknown. So in questions like this, what happens is the information they give you beyond the initial is to help you solve for various constants that come into play. Now, in our case, we only needed to solve for one parameter, So we just needed one piece of information. With that, now we can try to answer the question. How long does it take for half of the sugar to dissolve? So we're after a time. How long does it take? You know, what's the length of time? So our question is for what t, and we'll emphasize time, is a of t equal to a half. In other words, half has been dissolved. So what can we do? Well, we use either one. Well, I'll use the bottom one since that's probably the one most people will use. And we say, okay, that means a half, a0, is a0 e to the log of 3/4 times t. The a0's again cancel. So it doesn't depend on how much sugar there was. It'll still be the same answer whether there was a little bit of sugar or maybe you put in like 3 scoops of sugar. It's the same answer. We need to get the t out of the log. So we get log of 1/2 is equal to log of 3/4 times t. And then we divide and end up with t equals log of 1/2 over log of 3/4. You can pull minuses out, and if you do, so this is really minus log 2, this is minus log 4/3. This is the same as log of 2 over log of 4/3. And that's the answer. Now, it's not that unusual when dealing with an exponential type model to have your answers involve logs. So that's one of the reasons why you want to make sure you're very comfortable with using logs and all the rules that are related to logs. And so you don't want to feel like you're drowning in logs, going like log, 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 log. No. You want to be comfortable and make sure that you're doing well. So this brings us to the logistic model. We mentioned that in some cases the exponential model is a little bit unrealistic because it keeps growing unboundedly. And that's not how most things behave. Somehow, as you get larger, there should be some negative downward pressures on your growth. And so here's another model. And what this says is it says, oh, your death rate, it can actually rise faster when your population grows. So instead of being that the death is proportional to population, maybe it's proportional to the square of the population. Well, you might say that's unrealistic, but the nice thing is it's at least something we can work with, and so that's why we make that assumption. So when you plug that in, what ends up happening is it says, okay, so the population becomes k times p times m minus p, where k and m are constants. Now, if you were to cover up the m minus p, you say, oh, it's kind of behaving like an exponential, except you have this m minus p. Now, when does this come into play? Well, it comes into play relative to how close you are to p. How close m is to p. And so, if m equals p, that says, oh, somehow you've reached an ideal level of population. So when m equals p, you kind of level out. When m is bigger than p, well, that says, okay, there's still room to grow. And so you're going to move up. And when m is less than p, or if you like, p is bigger than m, somehow you've gone too big, and there's going to be some downward push. And so m is this sort of sweet spot. And we'll be able to make that more precise when we see the solution to the differential equation. So let's find the general solution to p prime equals k times p times m minus p. And at the end, we'll give an interpretation of m. All right. Now, here, let's add one more thing. Let's do what we did before, which is to say, throw an initial condition. The population at time 0 is p0. All right. So, how do we solve this? Well, there's two options. One way we could solve this is to say, oh, it's separable, which is we can put all the p's on one side and then everything else on the other side, and life is good, other than you have partial fractions. Now, does partial fractions scare us? Maybe. But we'll have plenty of chances to do partial fractions in the third part of this course, so let's not do that. Let us opt and do something else. What's the something else? Well, we can, if we expand it, say, oh, what do we have? Well, this becomes p prime is equal to, and I'll put this as kmp minus kp squared. Or, if you like, p prime subtract kmp is minus kp squared. And using our advanced thumb technology, if we covered up the p squared, we'd say, boy, that looks a lot like a linear first order. And because it would be. And we say, oh, wait, that means this is Bernoulli. So, okay, so let's use Bernoulli. So we get more practice, because who doesn't like more practice? We always love more practice. All right, so for me, what I like to do when I know it's Bernoulli is I say, I'm going to divide by this p squared. So, all right, so that says 1 over p squared p prime is minus km 1 over p, and that's going to be minus, whoops, not e, there's just a minus there. So 1 over p squared p prime minus km 1 over p equals minus k. All right, now the substitution. The way you find it is you say, look at the piece that used to become p, what's the power? This is going to be our substitution. All right, so we're going to substitute z is 1 over p, if you like, that's p to the minus 1. So then z prime, well, that would be minus p to the minus 2, right? Because you bring the minus 1 down, you subtract 1, that's to the minus 2. And don't forget the chain rule, because who would forget the chain rule? That's like a cool rule, times by the root of the inside, p prime. That's not p to the 1, that's p prime. All right, we say, well, gosh, that's an awful lot like this part right here. We have that p to the minus 2, that's 1 over p squared. We have the p prime. We don't have the minus. That's all right. Minus signs are easy to account for, so that's a minus z prime. All right, so updating, we have minus z prime minus k times m times z is minus k. Now, everything is negative, so let's make everything positive. We're the optimist. And now we're ready. And we're actually in good shape, because we already have a coefficient of 1 in front of our z prime. So we say, all right, come to our z, and we're going to do e to the integral of what's in front, km dt. Now remember, these are both constants. So this is an easy integral. It's e to the kmt. So this is our integrating factor, which we might call rho of t. And so if you multiply that through, we get that e to the kmt z prime plus k times m e to the kmt times z is equal to k e to the kmt. Remember, everything gets multiplied by the integrating factor. Everything on all of the sides. Yes, all 2 of the sides. That's right, all 2 sides. Well, why did we do that? Well, we did it because that makes this pretty. Namely, this becomes the derivative of e to the kmt times z. And now we say, well. Now we have one side that's easy to integrate, and the other side also turns out to be pretty easy to integrate. Wow, that's nice. We could hardly ask for anything more. So we say, all right, here we go. So we're going to do the integral of the left-hand side. Say, all right, whatever that's going to be, no, that's going to be easy, is equal to the integral of the right-hand side. All right, there we go. So on the left, it's e to the kmt times z. On the right, well, k and km are all constants. So you have a k, e to the kmt. You have to account for this km, so you divide by k times m. And don't forget you need a plus c. All right, now we're pretty close. We can now divide out by e to the kmt. And so that would get rid of the e to the kmt there. Here you can cancel off a k. So we'll go ahead and just mark that. You don't have to make the pa-chow sound, but you can if you want. 1 over m. And, all right, whoops. And now the c. Well, we have to have that. And remember, we're dividing by e to the kmt, so it's going to become e to the minus kmt. All right. Well, but we weren't asked to solve for z. Z was something we introduced. What were we asked to solve for? We were asked to solve for y. Well, sorry, not y, p. Ha ha ha, p. Well, what is the relationship between z and p? Well, z is 1 over p, and so we say, oh, that is 1 over p. Okay, well, we're pretty much in the home stretch, right? Well, so what do we have? We have 1 over p is 1 over m plus c e to the minus kmt. Now, the next thing we do is do things like flip both sides and start simplifying. But remember, we were going to solve for an initial condition. So let's go ahead and solve our initial conditions. Okay, so initial condition. What do we have? Well, we have 1 over p0 is 1 over m, and plus c, and then e to the minus k times m times 0. Well, k times m times 0 is 0, e to 0 is 1. Oh, okay, so that says c, well, that's 1 over p0, subtract 1 over m. Now, we can clean that up by combining it. So we could say, okay, common denominator would be m times p0. So then it would become m subtract p0 over m times p0. All right. So what do we have? Well, we have now the following. We're almost there. We're almost there. Okay. We have that 1 over p is equal to 1 over m plus m minus p0 over m p0 e to the minus kmt. All right, so that's what we have. Now, we can combine these terms on the right-hand side. Just get a common denominator of p0. So we have p0 plus m minus p0 e to the minus kmt divide by mp0. And remember, that's 1 over p. We needed to solve for p, so flip both sides, and we come to the conclusion that p is upstairs mp0, downstairs p0 plus m minus p0 e to the minus kmt. And we're done. We're done. Now you might notice something. This is more complicated than the exponential model in terms of the derivation and even the final expression. But you might say, okay, is it more realistic? Now that's a good question. So let's think about that. So we've copied the solution to the logistic model differential equation here. There's a couple of things you can look at. First off, if you plug in t equals 0, you'll see that you get e to the 0, which is 1. So you get p0 plus m minus p0. The p0's cancel, so you end up with m downstairs, and m over m is 1, giving you p0. So that's good. It matches the initial condition. No surprise, it should, because that's how we chose things to work out. But things get more interesting when you start saying, okay, what is M? So that was a question that we didn't quite answer. What is M? How should we think about it? Well, when we start looking at what's going on, we can see a couple of things. Let's let now T get large. Okay, so let's assume here for a second K is positive. All right, that's a pretty reasonable assumption. Then we have e to a negative number. And in the long run, that's going to go to 0. So what happens is everything attached to that goes to 0. And so we have mp0 divided by p0, which is m. So when k is greater than 0, then what we have is that as t goes to infinity, p approaches m. Now there's some caveats here. I'm sweeping details under the rug. But let me show you what I mean by that. So here we'll draw a population. So we have m. And you'll see if we plug in p equals m, the right-hand side is 0, and the derivative of a constant is 0. So in fact, this is a solution. It always is. It's a stable solution. We'll talk more about that in a future class. And what happens is that if we start below, we are going to be drifting up. So starting from down below, our population moves up towards m. If our population is below m. If our population is above m, then what will happen is we'll move towards it. So m you can think of as the long run. What's going to happen to the population in the long run? And it's sort of what I like to call carrying capacity. It's a word that sort of captures, that says, oh, if you have an environment, how much population can the environment support and sustain? So M is the answer. It's the ideal level of population. There's no incentive to decrease. There's no incentive to increase. Now, there are some caveats where it says, well, what if you start with a negative population? Well, if you run the math, what will happen is you'll actually head off in that direction, which is probably not realistic, but that's all right. The odds are very good we aren't starting with a negative population unless somehow we have a zombie apocalypse, but that would be a completely different kind of a class. All right, well, what happens if k is negative? Well, then things sort of switch. And if you think about what we were talking about with the exponential model, k is positive in the exponential model meant we had growth. When k is negative, we had some sort of decline. It turns out that, again, if you plug in m, we do have a solution. But now, if we're just below m, we actually move away and we head towards 0. What happens if we're just above m? We are going to blow up. And I mean that not just figuratively, in that there's an asymptote. And we will, in a finite amount of time, the solution will head off to infinity. And you can see that, and what will happen here is that we'll have the m minus p0 will be a negative, and this is a positive, and by choosing just the right value for t, we can get a division by 0. So there can be very drastically different situations depending upon if k is positive or negative. You should essentially say the default is k is positive. And because this is the type of situation that we tend to typically associate with populations. All right, so what is m? I didn't write that down, but I said it out loud, so I should write that down. We think of m as, I'll call it carrying capacity. How much can your environment support? And there we go. So let's do one final problem. And this one relates to the logistic model. Suppose that the population of a country in millions follows p prime is k times p times 200 minus p, where k is a constant. And its population in 1960 was 100 million, and was then growing at a rate of 1 million per year. Predict the country's population for the year 2020. All right, good. So what do we have? Well, we have a logistic model. Now, the good news is we're not going to ask you to memorize the logistic model, but in other words, we're not going to ask you to memorize the solution. So let's start by copying down our solution. So we can just grab one of the pages that we recently worked on. We can say, okay, so if we have P prime is equal to K, P, M minus P, and P of 0 equals, P naught equals P of 0, then the logistic model, we're going to copy it down, tells us that our population should behave like MP0 over P0 plus M minus P0 e to the minus KMT. All right, so that's just a given. So we don't have to rederive that. So what do we need to do? We need to know how to use it. And that can be just as challenging sometimes. You say, all right, well, what can we do? We notice a few things. See how there's an M here, and there's a 200 in the right spot? So we know from the start, M is 200. Good. Progress. All right, so that's something useful. We also know its population in 1960. So we'll think of 1960. We'll think of this as time equals 0. So our P0 was 100 million. So let's just drop the million. And so we'll say our P0 is 100. We can always put it back in the million later on. So our units are in terms of millions of people. All right, great. Now we have one more phrase. Okay, so was growing at the rate of 1 million people per year. Now, what does that tell us, and how do we get there? So we know something about the rate of growth of population. Does that say that K is 1? And why not? Okay, so it doesn't say that K is 1. We have to be careful here. What is it saying? Well, it's a rate of growth, because we see the word rate. When we see the word rate, we think derivative. So I say, oh, all right, so what we know is that 1, that's our rate of growth, is P prime of 0. All right, so that's what that sentence is saying. Now, how can we take that? Well, do we have any knowledge about P prime? We do. It's right there. There's a differential equation. So, so that becomes some constant, which we don't know, times P of 0 times 200 minus P of 0. All right. But we do know what the population is at time 0. We know it's 100. So 1 is equal to K times 100 times 200 minus 100, which is times another 100. Or what we get is that K is 1 over 100 squared, which is 10,000. There we go. All right, so that's K. So K is 1 over 10,000. So here we're using the differential equation to solve for K. All right, so if you're given information about derivative, use the differential equation to help solve for constants. Nice. All right, so now we have our P, and we just found we have our M, we have our K, and what do we need? Well, we need our population in the year 2020. Wow. To think, what will life be like in the year 2020? Who knows? Who knows? Well, if we're patient, someday we'll find out. All right, so what does that correspond to? Well, that corresponds to t equals 60. Because we set t equals 0 to be 1960, so 2020 is 60 years later. So now we plug in what we know. We know we have P, our population, is M, which is 200, times our P0, which is 100, over our P0, which is 100, plus our m minus P0, 200 minus 100, which is 100. And then we have e to the minus k, 1 over 10,000, times m, which is 200, times t. All right, we can clean that expression up. Certainly, all these hundreds can cancel, so we end up with 200. Divide that by 1 plus, now here we can cancel off some zeros, so you end up with 2 over 100. That can be written as e to the minus t over 50. All right, so that's our population at any time. Now we plug in times 60, and what do we get? Well, our population in the year 2020 is 200 over 1 plus e minus 60 over 50, which will be 200 over 1 plus e to the minus 6/5. And that's the answer. Now you might say, well, wait, what is that number? Well, that's a calculator question, and that we're not a calculator kind of class, at least not at this point. We're just learning to use it. And we could, if we wanted to, say, as a reminder, this is millions, and well, it's certainly not up to 200 yet, but all right, it's something. It's, notice that e to the minus 6 over 5, that's less than 2, and so it's going to be more than 100, so that's good. And well, there we go, right? That's the kind of questions that we can answer. Okay, well, that was good practice. Life is good. Now we have another thing we can talk about in terms of applications, population. And so, great. Thanks for joining, and we'll see you again soon. Bye.